Hi, welcome to physics lesson. Today we'll have a quick revision for chapter 7. For Form 4 students, you have learned chapter 1 to 10 in textbook 2. Actually, chapter 7 is quite important. For chapter 7.1, conservation of momentum. That is the equation m1 u1 plus m2 u2. Okay, that is the total momentum of the system before the collision would equal to m1 v1 plus m2 v2. Okay, the total momentum after the collision. Where will you use conservation of momentum? It will be a collision case, or explosion, or shooting. For these cases, we will use conservation of momentum. Okay. Like for experiment 7a, you can see the trolley crash. For this case, we will say case A is stick together after the collision. So by conservation of momentum, we will have this equation m1 m2 m1 u2 m1 u1 plus m2 m2 u2. Okay, that is the total momentum before the collision here, will be equal to m1 plus m2 v, because they have the common final velocity as they stick together. Okay. Okay, we go further. Okay. For the experiment, actually we can show that the total momentum is conserved. And what is momentum? Here, momentum will refer about the product of mass and velocity. Mass times velocity. So velocity is a scalar. Sorry, it's a vector. So momentum will also be a vector. That means we have direction. And maybe if we take right x positive, then the total then the momentum will be positive, will be to the right hand side. Okay, if the momentum is negative, that means the velocity would be to the left. Okay, so we have to think about the direction, very important. Otherwise, for the substitution, you may get a wrong answer. Example 1, okay, find the momentum and total momentum. Very easy. So you see here the dot. Okay, the dot here. The momentum. Now maybe we take left x positive. Actually, you can take right x positive. It depends on your definition at the beginning. So the total momentum here for the dot will be a bias value, because we take right x positive. Okay, take right x positive. For Tom momentum, so it will be 50 times 2. Okay, we use positive 2 here. So the total momentum of the system, it would be sum of them. Okay, so the total value will be 20. Now suppose the dot stick with the Tom. Okay, stick with Tom. That means they have the common velocity. So what is the common velocity? Okay, after the collision, okay, they stick together. What is the final velocity? So very easy. m1 u1 plus m2 u2 equal to m1 v1 plus m2 v2. Okay, this is the conservation of momentum. So 20 equal to for Tom 50 v plus 20 v. So we get 20 over 70 v here. Okay, so they will stick together and move to the left with the speed 2 over 7. Okay, because we take left x positive, so direction is left. Okay, now this is the complete answer. Now this is a typical case collision. So you should be aware of the direction. Otherwise, you would get an incorrect answer. Okay, and then we go further. A law of conservation of momentum. Actually, we have discussed before. Experiment 7b, some more crash. Now, maybe after the collision, two trolley would move with a different velocity. Okay, but by the data, we can show that the total momentum of the system is conserved. We go to the third case, explosion. Okay, if the two car here is stick together at the beginning, okay, we'll say before collision. After we hit the button, okay, the spring inside would make the trolleys to move. Okay, the trolley will move in opposite direction here. Now, this is collision. This is explosion. So we can also use total momentum to be conserved. It would be total momentum. What do you think about the total momentum before the explosion? M1 plus U, M1 U1 plus M2 U2. Okay, that is very easy, 0. Equal to M1 V1 plus M2 V2. So we can find out the speed after the collision, after the explosion. Okay, if they have same masses, they will have the same speed. Okay, and we can also find out the speed after the explosion if we know the masses. For chapter 7.1, apart from conservation of momentum, we have to study one more thing, which is very important. That is we have to distinguish elastic collision or inelastic collision. Okay, elastic collision or inelastic collision. Sometimes maybe we will think about the completely inelastic collision, but actually it belongs to an inelastic collision. Okay, the key word to distinguish between them is the total KE of the system. Okay, suppose we have a car collide with another car. Okay, so if this collision, if the total KE of the system after the collision is conserved, that means the total KE of the system is unchanged. That means low energy loss during the collision. We will say is elastic collision. Otherwise, if there is a KE loss of the system, we will say this is an inelastic collision. Now maybe we take one example. Say car A has 1,000 kg, and car B say 2,000 kg. Okay, if the car A, car B, if car A has a speed say 10 ms mass 1, okay, after the collision, if car A stop, okay, V1 0. Okay, so what is the speed of car B? So it will be easy because we can think about the total momentum. The total momentum before collision, that means the left hand side here, okay, left hand side here, it would be 10,000, right? 1,000 times 10, okay, per 0. So after the collision, we will know that car B will move at a speed of 5 ms mass 1. Okay, do you think it has KE loss or no KE loss? Maybe we can calculate it. Okay, now before collision, the total KE will be 1/2 times 1,000 times 10 square. Okay, per 0. So it will be equal to 50,000 joule. Okay. After collision, what can you get? 1 over 2, 2005 square. Okay. So it will be 25,000 joule after collision. So when you compare the total momentum, that means the when you think about the total KE of the system, that means the KE of both A and B. Okay, so you can see there will be a decrease in KE of the system. So it belongs to inelastic collision. Okay. Now, if you calculate the total KE is unchanged, that means it will be elastic collision. Okay. If all the KE is lost, it will become a perfectly inelastic collision. Say if a ball, say if a ball drop down to the ground and rebounds, okay, a ball drop down to the ground and rebounds. If it can rebound with the same height, that means it's elastic collision, low KE loss. Okay, PE change to KE and then go back to the original position. That means low KE loss during this collision. If the ball drop down to the ground, but after rebounds, it cannot go back to the original position, that means it's in elastic collision. Okay. If the ball drop down to the ground and then there is no rebound, so that means it is completely or we say perfectly in elastic collision. That means all the KE is lost, will be changed to heat energy, sine energy. Okay. The type of elastic collision or inelastic collision is different from total momentum. Okay, two cases. So we can think one by one. That means we can think we have two points to think. Point one is we need to know whether the total momentum is conserved or not. Point two, we need to calculate whether the total KE is conserved or not. They have no relationship actually. Okay, two cases, two different cases. If for this collision, completely elastic collision, explosion, okay, of them, for some condition, we can have total momentum to be conserved. Okay, but the total KE only conserved for elastic collision. Okay, for elastic collision, that means low KE loss. Okay, it will based on your calculation. So remember, you have to calculate the total KE of the system. If the question is asking you about the type of collision, total momentum of the system. Here the equation. Okay, as we have talked before. Total momentum. Okay, now maybe we try chapter 1 first. You must have a try. Classify the following collision. Okay, that means you have to think about the type of collision, elastic or inelastic. Okay, now let's check inelastic. Okay, now so you have to calculate the total KE of ball A and ball B. Okay, before collision and after collision. So you can find that there is a decrease in total KE, so in elastic collision. For case B, elastic collision. Okay, like maybe you can check. The total KE before and after collision are the same. Total momentum is always conserved. The answer is no. Okay, now we have a criteria and we will talk it later. Option 3. Okay, and total KE of the system is always conserved in elastic collision. Actually, we will say this is definition of elastic collision. Total KE is not conserved in elastic collision, yes, because there is a loss in KE. Okay, when object X collide with object Y, total momentum of X is not conserved, yes, okay, because there is a change in velocity. As we know, the momentum is the product of mass and velocity. Okay, collision, so you know X may be slowed down. Okay, and also you can use apply the law of conservation of momentum to find the answer. Okay, maybe you have a try and check the answer. Okay, this is one example. Okay, and the example. Examples for conservation of momentum with a toy. This is the Newton's cradle. Okay, like it's funny. If I raise one ball here, okay, and then I release the ball, and then you collide with ball 2. Okay, this is ball 1, ball 2, 3, 4, 5. Okay, so it would collide with ball 2, say speed v. Okay, speed v. So what is the total momentum before the collision? Suppose the ball has a mass of m. Okay, each of the balls has mass of m. So answer is easy. It will be mv before collision. Okay, after collision, what do you know? Now we have learned total momentum to be conserved. So after collision, the total momentum would be also equal to mv. Okay, so that means before collision total momentum, after also equal to mv. Okay, so you can predict the movement of the ball. You will become ball 1, ball 2, ball 3, ball 4 all at rest, but ball 5 would rise for the same height. Okay, because the ball 5 would move at a speed of v also. So you can go back to the original position of ball 1. Okay, I mean the height, the same height as ball 1. Okay, if low air resistance, if low sound energy is lost, the process will be repeat. Ball 5 drop down and hit the system. The remaining balls, ball 1 will go back to the original position. Okay, so this is a toy for checking or for seeing the conservation of momentum. Newton's cradle. Okay. Recoil of gun and cannons. If we shoot a bullet by a gun, okay, so we would have a recoil velocity. That means the gun moves backward. Okay, we can calculate the recoil velocity very easy. Suppose the bullet has 0.1 kg. Okay, and the gun has 0.9 kg. So before shooting, what do you think? The total momentum, it will be 0. Okay, after shooting, what is the total momentum? Now say the bullet has a speed of 200 ms mass 1. So it will be m1 v1 plus m2 v2. So it will be 0.1 times 200 plus 0.9 v2. Okay. So 20 plus 0.9 v2 equal to 0. Okay. So V2 will be equal to 22, okay, minus ms minus 1. Okay, we can find out the recoil velocity, and the direction you see is negative value, so that means left, okay, because we take right as positive. Now this is recoil velocity. And similarly, we can think about the cannonball. It will be the same. The cannon, after shooting, the cannon would be would move backward, okay? And we will find some DSC and also CE questions about this case. Very important for chapter 7.1, total momentum, okay, type of collision. Spacecraft, okay, how can astronaut move in the space? It will be very easy, very funny. Okay, the spacecraft eject mass of hot gas backward in the space. So by the conservation of momentum, we would know spacecraft move forward. Okay, do you agree? If the spacecraft here, okay, eject air, hot gas actually, backward. So the spacecraft will move with a forward speed. Okay, V1, V2. Before we start the engine, the total momentum, you may regard the total momentum to be 0 in this case. Okay, so by the conservation of momentum, we can find out the final speed of the spacecraft. Okay, similarly, astronaut would have the same idea. Astronaut can go back to the station from the space by eject gas in different direction. Okay, actually in opposite direction. Total momentum. This is the most important point. We have studied the type of collision, and also we have studied the law of conservation momentum. But how can we? What is the condition for using the total momentum to be conserved? Okay, its total momentum must be conserved. There will be one important point you must highlight this. If there is no external force, for example, friction, no friction of the acting on the system, then the total momentum can be conserved. Otherwise, if there will be an external force acting on the system, the total momentum is not conserved. Okay? Now, for example, if a car collides with another car B, okay, car A collides with car B, we can calculate the final velocity after the collision. However, if the ground has friction, okay, it's friction, so the total momentum cannot be conserved because the total momentum, because the friction will be the other parties of the system. We may talk about it in the chapter 7.2. Okay, there will be a calculation for this. Okay, try chapter 2. Okay, like you may pause the video and try chapter 2. Okay, like this is the answers. This is the end of chapter 7.1. Maybe you can try all the questions. Okay, you may check the answer from the eClass. You can download the answer from the eClass. It will be the full solution. Chapter 7.2, change in momentum. Okay, quite important here. We know F equal to ma, okay, and A will be equal to V minus U over T. So, and we can have F equal to mv minus mu over T. That means weight of change in momentum. We say weight of change in momentum. rate of change in momentum. Okay, now we can say a net force is rate of change in momentum. And this is a new definition for chapter 7 for net force. Okay, so if we know the momentum change and the time, we can find out the net force. Example, change in momentum. Okay, not quite important. We go further. Conservation of momentum. For chapter 7.2, you can see there is a proof for the equation. Before collision here, so you see the ball ball A, okay, move with UA, ball B, MB move with UB. Okay, after the collision, we get VA, VB. Okay, during the collision, we find there will be a net force acting on each box. Okay, each ball actually, each ball there will be the force on A by B, and also force on B by A. So do you think what is the relationship between them? Force on A by B versus force on B by A. The answer is they are equal but opposite in direction by third law. Okay, actually we use third law to derive the law of conservation of momentum. Okay, so we get here. Okay, F on A by B equal to minus F on B by A. So by substitution, okay, MV rates of change of momentum, MAVA minus MAUA over T equal to minus MBVB minus MBUB over T. So we can have the law of conservation of momentum. So you see, this law actually based on third law. Okay, but we have a criteria for using this equation. That is, you must know external force acting on the system. Okay, we just consider A and B. Force on A by B, force on B by A. Okay, we don't think about there is an object C here. So no friction, no gravity affecting the speed. Example line, okay. Now checkpoint 3, have a try by yourself. You will find the solution here. Impact. Now this is quite important. This is quite important. Force of impact. We can use motion sensor to find the velocity of the trolley, and we can also use force sensor to measure the force acting on the trolley. Okay. So we have a very important graph that is FT graph. 7.2 actually focus on FT graph. For study about the graph, we will think in two ways. One way is to think about the slope, and that would be think about the area. Now, area has a meaning, has a physical meaning. What do you know what is it? Maybe we FT area, F times T. So what does it mean? By the equation F equal to mv minus mu over T. Okay, that is the beginning point in chapter 7.2. Rates of change in momentum equal to net force. So Ft will be equal to mv minus mu. That is change in momentum. Okay, the FT graph has a physical, the area under FT graph has a physical meaning. The meaning is equal to weights, equal to a change in momentum, change in momentum. And in physics, we would use another name for change in momentum. And you need to memorize that is impulse. Okay, if you see impulse, that means change in momentum. It's a physical meaning, change in momentum. Okay, FT graph. You can see here. Okay, why will it be important? You may think if there's a car, okay, hit the wall, okay, there is an accident here, okay. Now without seatbelt, without wearing seatbelts for the driver, okay, so we can have this FT graph. Oh, what happened? Oh, okay. Now we have this FT graph. So the driver may die because there is a large force acting on him. However, if he wear seatbelt, okay, so it would lengthen the time of impact. By using this equation, F equal to mv minus mu over t. Okay, Ft equal to mv minus mu. Okay, actually after the collision, v will be 0. Okay, u is the initial speed. So that means change in momentum is constant for these two cases. So if the time is lengthened, mv minus mu equal, it will be the same for both cases. If the time is lengthened, that means the time is longer. So the FH force will be smaller. Okay. The total momentum is the change in momentum is the same. So the area will be unchanged. So now if we have seatbelt wearing by the driver, so the force will be that. Okay. So you see the time of the collision will become longer. Okay. However, the area will be the same compared to two graphs. This area will be the same. Okay. So the maximum force acting on the driver will be smaller. Same area, longer time. Okay. That means the peak value, the maximum value of the force will be smaller. Okay. Now suppose they have the same idea, because change in momentum is the same. V is 0. U is the initial speed. Okay. Which is also unchanged. Time of impact. So we need to design something to lengthen the time of impact. So we can have a smaller net force. Okay, smaller FH force. So you see, for fixed change in momentum, the net force is larger if time is short. Okay, so to reduce the force of impact, we need to think about how to lengthen the time of impact. There are two examples, so please pay attention for this. Maybe you should underline them. Front and wheel part. Okay, front and wheel part. Okay, the end of the car, wheel part. Okay. We will say the compound zones, okay, can deform in accident. During the collision, it deform. The deform means it can lengthen the time of impact. Okay, before the car come to stop. Okay, lengthen the time of impact. Another example, crash cushion system. Okay, like you may see this in the highway of the in the highway. Okay, and it can be deformed. Okay, same idea, lengthen the time of impact. Okay, so the impact force will be smaller. Okay, then you can drop down the final result. Impact force will be decreased because time of impact is lengthened. Okay. Chapter 4. Have a try. I will say question 2 will be important. Okay. Area of FT graph, you can find a change in momentum. And also by F equal to mv minus mu over t, you can find the net force, FH net force. Okay. And for question 2, tennis ball drop from a certain height onto the top pan of balance. What does the balance measure during the collision? So you will know that during the collision, there will be two forces, R and also weight. Okay, R, but here R is not equal to weight. R during the collision, you know R is greater than weight. R minus R minus mg equal to mv minus mu over t. Okay, the balance measure R. That is the force on ball by pen, or it will be the same on pen by ball. Okay, because action reaction pair. So not A, not weight, just the weight of ball. Not C, not the net force. Okay, we should think about there is a weight acting. There is a weight acting on the ball. Not change in momentum. Practice 7.2. Try MC questions. Okay. So it's not quite difficult, right? Maybe we have a final quick review. 7.1, you have learned momentum. You have learned conservation of momentum. There is an equation. There is an equation here. You have you have studied the type of collision. Okay, type of collision. Momentum. Okay, like two different things. Don't mix it up. You know you have learned two things in chapter 7.1. Okay, 1 point, 2 point. Change in momentum 7.2. And we have learned FT graph means change in momentum. And in DSC, we may use impulse to represent change in momentum. They are the same actually. And also, if we lengthen the time of impact, the impact force will be decreased. Okay, now that's all we've learned in momentum. Okay, for the momentum, you should know that if we can see a case collision or explosion or shooting or explosion, okay, we will apply conservation of momentum to calculate its velocity. Okay, maybe you can try these questions. I would think the past paper questions are quite important. So you must try. Question 18, 19. Okay. For the answer, 18 will be boy, 19 C. And also try question 20, conservation of momentum, 22, 21. Okay, tell me if you have any problem. Okay, and question 30 is a very good question. Okay, typical question. We may find this from the past paper. Okay, DSC type question, 30. And also 37, must try question. Okay. Don't miss the past paper. Question 38, 39. And also 40, 41. You may check the marking scheme from ECAS. Okay. I've posted a textbook solution and also the CE DSC marking scheme in the ECAS. So have a check. Okay. And finally, self-test. Do you have 40 minutes? 20 minutes. So question 1 to 4, MC. Okay, checking. You can check the answer here or at the end of the textbook. Okay, and section B. Can you calculate this answer? Okay. Now the last important thing is what is the condition for using conservation of momentum? Okay, the answer is if there is no external force, we can apply this